Okay, so we've talked a little bit about the purpose of a business is to make money. We've talked a little bit about arbitrage. Okay. Arbitrage is where you have two different commodities and you exchange one for another, and there's a relationship of how they work and what their prices are. The next one I want to hit on is fiduciary responsibility. Before we talk about Merkle Trees, fiduciary responsibility. If you take somebody else's money and you have a company that you are using their capital, you are legally required to have fiduciary responsibility. That means you, as the person running the business, are now legally required to do those things that do what? Back here, the purpose of a business is to make money. So if you can take your stuff and you can produce your stuff at a cheaper cost, say in Alabama than in Wyoming, and this is a good move for the business, okay, because it makes more money, you are legally required to do it. Now, if that means that you have 1,000 people out there working in your workforce, and you can take those 1,000 people and replace them with a bunch of robots on your production line, and fire the people, save a bunch of money, you are legally required to do it. Okay, remember, the purpose of a business is not to hire employees. It's not to take care of them. It is to make money. So, when you hear about people saying, well, the business should, the legal responsibility as it stands in the United States is fiduciary responsibility. We want to talk about Merkle Trees. Okay, so we have a block, and this is probably a struct in Go that has some fields in it. But we've taken that struct and we've run it through a piece of code that has serialized it down to a slice of byte. And so it's a whole bunch of bytes now. We don't care what is in it, just as long as if we change something in here, it ends up being in here and gets changed in here. That's all we care. And we have a bunch of these things. I'll draw, I think I did 5. 1, 2, 3, 4, 5. Okay, continuing. Long gap, had to go get some water. Okay, we've got 5 of these chunks of bytes. And we can say that this data type is now a slice of slices of byte. Okay? So, because we've got multiple pieces and they're all bytes. And then we take each one of these and we run it through our h function, our hash function, and out of that we get new slices of bytes. So at the end of this, we should have the same number in this array index. So this is a slice of byte. So each one of these leaves, we get converted to this. Now we want to take pairs. And if we have an odd number out here, we want to just use that one by itself. But otherwise, we'll take pairs, we'll run the 2 of them through our hash function, and we will end up with a slice of bytes. And the odd one, if there's one, we just run it through the hash function. We get the same thing. So our data type is the same on the output. So what we're going to do with our slice of bytes is we're just going to swap it and we're going to do it again. So now we've gone from 5 to 3. Now here we do the same thing. We run these 2 through our function. We run this one through our function again. To 2. And then now it's inevitable that at some point we're going to get down to, yes, a final result where we do the hash function on the 2 of them together, and we end up with just 1. And that 1 is our final result in our Merkle tree. So from implementing in Go as a function, what we want to do is we want to take in a function that takes as an input a slice of byte, so that we can collect the pieces, put them all together, and we can take these things and pass it in. And we've got one phase where we take the original data and we turn it into new data, but we end up with the same number. So we've got the leaf piece. And then once we get through that, each time we're going to take our input, we're going to run through it, and we're going to end up with a smaller number, and a smaller number, and a smaller number, until we get down to just one value, and then we return. Now, in your notes, I've given you the pseudocode for doing this, and I believe the function declaration in the code in GitHub, there's not just that. There is all the pieces with a test piece of code and sample data so that you can actually test that this piece of code works. And in the bigger picture, in our blocks in our blockchain, we're going to have transactions, and each one of these transactions is going to go through the Merkle hash, which puts a hash back into our block. Then we have a nonce and a seal. And we take those things and we turn that into the eventual seal on the block through a mining process. And that is the block that we write out when we find out what we're looking for. Now, how secure is this Merkle process? This Merkle process has actually been mathematically proven to be more secure than just hashing everything together. One of those things in our transactions is we have a sequence number of the position in the transaction that gets part of this. So you can't flip the sequence of any transactions. So their position is fixed, the data in them is fixed. All of this stuff comes into a Merkle hash. That Merkle hash is hashed with the rest of the information in the block to produce the seal. The seal is then manipulated with the nonce to do the mining, and we end up with a final result. So this is the security that goes into making certain that nobody changes the data, that the data is accurate, that it's immutable in a blockchain. But this is the piece. And that's the second part of your home or your assignment, is to implement this. Performance-wise, I think I mentioned that this implementation is fast. It's substantially faster than a similar implementation. I've tried Go libraries with this, where they take their structures and they're going to hash all the stuff, and they're going to have pointers and memory allocation. And you know what? Just convert it to bytes. And just hash it as bytes and just run through it as arrays. And we're kind of doing a tree. We're doing it from the leaves down to the root of the tree. I think that's the way we want to describe that. And it relies on careful implementation of manipulation of slices of bytes. And it's not long. Doing it this way is a short piece of code. So that's what's up with the Merkle trees and that part of the assignment. And I think I'm actually going to do a walkthrough of the actual pseudocode, but not during this lecture.